Okay. So one of the most popular and some sense mind blowing thing with the ensemble method space, right. So boosting, in fact the original boosting work, original analysis of the boosting work comes from theoretical computer science community, not necessarily from an empirical machine learning community, right. So therefore they were that they looked at having some oracle that had a probability slightly greater than 0.5 of being correct, right, and then they tried to see how you can get better and better predictions from somebody who is just above 0.5, right. By combining many such oracles, right, I can keep improving my accuracy of prediction arbitrarily close to 1, right. So that is the amazing part, right. I start off with each individual predictor has accuracy of 0.5 plus some epsilon, okay. Just better than random, right. I can combine a lot of them together and produce something that has accuracy close to 1, right. So this was a very big result that came out earlier, and so we are going to look at some kind of simplified version of it. So remember the goal that distinguishes, I mean the main thing that distinguishes boosting from the other methods is that boosting is inherently serial, okay. So boosting is going to build this ensemble classifier in an incremental fashion, right, where at each stage I am going to try and explicitly reduce the error produced by the previous stage, right. So this is something that you have to keep in mind. You just can't write, you just can't come up with some ensemble method and call it a boosting method, right. I have seen that happen in many papers that I have reviewed, right. People just write something that has multiple classifiers in it, so it is boosting, because they have read somewhere that boosting is a very hot area and people papers in boosting get accepted. So they come up with any classifier and any ensemble method and call it boosting. Boosting has this very specific property that at every stage, right, you add one more classifier to the existing ensemble, right, and this is done in such a fashion as to reduce the error produced by the classifier up till that point. Okay, make sense? Sorry? You get a choice as to what to add next, right. So that is that you choose it such a way that you minimize the error that you have, not at least you reduce the error, okay. So not necessarily minimize, but you reduce the error of whatever has happened the prediction till that point, okay. Does that make sense? Okay, so that is essentially what boosting is. Sometimes you can think of it as error boosting, sometimes they call it as error boosting and so on and so forth. The one very popular and one of the original boosting algorithms is called add a boost. Right. So let's I am just going to put up a tutorial for you guys to refer to, okay. I will use the notation from the tutorial, so I will not translate it to the notation in the textbook, okay. So when you read the textbook you have to do the translation yourself, okay. So that is one of the main problems when you have too many different disciplines contributing to the same field, right. Machine learning has people from computer vision, people from statistics, people from AI and all other disciplines contributing to it, and each one of them brings their own notation to the mix, right. So it becomes harder to keep track of everything, but I can leave the I out, okay. It's unnecessarily complicating matters. Okay. So I am going to denote by C subscript X the m minus 1th stage classifier, okay. That is obtained by basically adding the outputs of all these individual classifiers. So, the alpha 1, alpha 2 to alpha m minus 1, right. So, I am going to add up, these are the weights, and K1 is a classifier that I added in the first stage, right. K2 is the classifier I added in the second stage, and so on and so forth, and Km minus 1 is the classifier added in the m minus 1th stage, okay. And basically I want to produce that okay. Yeah, the rest of the class. So, there are a couple of things which I should point out here. One of the most obvious ways of doing this, forget about databooks, one of the most obvious ways of doing this is to say that, okay, I am going to take this guy, right, look at the residual error, you know, I can think of this as a prediction problem, right, and look at the residual error of the predictor, right, and then train a classifier Km to minimize the residual error, right. So, what will be my alpha m? Essentially you have to make sure that this whole thing is along the direction of the residual. So, we talked about this earlier, right, where did we talk about this? Forward stage, yes, stage wise or stepwise? Stage wise. Right. So, when we talked about stage wise feature selection, we talked about something similar, right. So, you could think of something along the same lines here. Instead of thinking of selecting features, right, I am just selecting classifiers, right. So, I can just take the residual error of Cm minus 1 and then use that to train Kmx and then add it here, right. In fact, this can be 1, this can be 1, does not matter, because the Km of x will actually align itself in the direction of the residual. So, I can just add it here, so that is fine, right. So, that is the simplest way to do this thing, and it is actually a good way to do it if you are doing regression, okay. Does that make sense, right. I can take this as I can take the residual error and then train my Km to actually go in the direction of the residual error. So, I can actually do this, so I can get a boosting like algorithm for regression just by training it along the direction of the residual, right. But when I am doing classification, that is not necessarily the right thing to do. So, people come up with different kinds of loss functions and then they try to improve the classification. So, the loss function we will look at is the exponential loss. Do people remember the exponential loss? I talked about it when we are doing SVMs. That is the exponential loss. Okay, e power minus yi f of xi. Right, so, we looked at the exponential loss earlier. So, we will essentially continue with that. So, I will sum over all the training points. Right. So, that is the exponential loss for the mth stage classifier, right. People agree with me on that? Okay, so that is essentially what I wanted to write, right, and I have expanded the Cm and I have written it as this expression in the bracket here. Yet can people see me at the back? See, not me, but the I am kind of hard to miss, right? That makes sense? Okay, great. So this thing we already know, right? So there is no control we have over that. That thing we already know, that's given to us. All we need to find is alpha m and km, right? So I am going to rewrite this as what's that? That's the loss function we are going to be using, right? That's the exponential loss function. So for classification, we looked at, if you remember, we looked at the different loss functions and when we looked at hinge loss, right? And I said exponential loss is one of the loss functions, and this is how we defined it. So essentially, I am using that exponential loss function here. And in fact, I mean, this was not the way AdaBoost was originally derived. Okay, AdaBoost was derived in a completely different way, and later on, about 5 years after they published AdaBoost, they kind of discovered the connection between this kind of stage wise modeling, right, forward additive stage wise additive modeling and exponential loss. They said, okay, I can do forward stage wise modeling with an exponential loss function, I end up with AdaBoost, and that connection was discovered 5 years later, but now almost always people except in the theory community, in the machine learning community, it is always introduced like this. Okay. So where WMI is sorry. The same thing I wrote here. So the weight of the ith data point at the mth stage, right? The weight of the ith data point at the mth stage is essentially e power minus yi cm minus 1 of xi, right? So what does this mean? What is exactly this expression, if you think about it? It is the loss I have incurred on that point xi up till the m minus 1 stage, right? That is essentially that, right? Just the loss that I have incurred on the ith data point up till the stage m minus 1, right? Okay, now I am going to break that sum up into two components. So what do you think of these two components?
Bias and variance?
No. This varies here, e power alpha m anything. So when will I get e power minus alpha m? When I have correctly classified it. When I will get e power alpha m when I have misclassified it. So these are all the data points such that right. These are all the correctly classified data points. These are all the misclassified data points, right. This intuitively you can see where we are going with this. So what is the best classifier that I can find at the mth stage? Well, obviously the best classifier I can find the one for which this summation is empty, done, right. I mean, get everything correct, classified correctly, so that is the best classifier. But now is the crux, right. Remember, our classifiers are all weak classifiers, right? At least that is the basic assumption we are starting off with, right. The classifiers are all weak classifiers. I can do only slightly better than random, so I have to get nearly half the data points incorrect, right. So which half should go here, which half should come here, and then we can move one data point from here, that to here, to make it better than half. Right. So which half should go here, which half should come here? Intuitively tell me, which one will incur less penalty? What is small? It's half, man. What is small half? You have to be more clear to me. You have to be more clear as to what is small means. No, there is a valid way of interpreting small half. Tell me what is that? Huh? No. WMs. Right. So all the W's that have a large value should come here because they get multiplied by e power minus alpha. The W's that have a small value should go there because they get multiplied by e power alpha m. So what are W's with small values? The ones that I have correctly classified up till the previous point. W's with a large value are the ones that I have incorrectly classified up to the previous point. So at the mth stage, what I should be looking at is try to get the data points which I misclassified from the previous stage, try to get them correctly, as many as possible, right. So that is essentially the intuition behind AdaBoost. So at every stage what you do is you try to look at the previous stage, see which are the data points you misclassified, you try to get them correctly in this stage, right. And it is okay if you make mistakes on data points that you have correctly classified till the previous stage. Why is it okay? Well, because those classifiers can possibly adjust for it, okay. Then we will look at how we will actually do this again, right. So I am going to call so all the weights of all the data points I got correct at the m stage, right. Likewise weight of all the data points I made a mistake on at the m stage, right. So then I can write my E as simply as okay. So if you think about it, the value of alpha really does not matter in my choice of Km, right, regardless of the value of alpha, right, regardless of value of alpha m, whatever argument I gave you just now holds, right. The idea is to see how much of the weight you can push to Wc, right, and how less of the weight you keep in Wv. I mean there is total of weight, right, there is some total W, right, W is a constant, right, Wc plus Wv is a constant. constant. This is a constant. So the goal is now to see how much weight you can push into WC as opposed to WE. That's basically the classifier that we are going to do. But Km will be a classifier that tries to put as much weight into WC as opposed to WE. So how will you do this? Well, you can use the classifier that can assign weights to data points. We discussed this very briefly in the decision tree case, right? You can assign weights to data points, and you can essentially multiply the error that you make on a data point by the corresponding weight. Right? So the error that you make, you multiply by the corresponding weight, so that will give you the weighted minimizer. Right? There are other ways of doing this. So one way, so people see what I am saying about Km, right? So you see what you are supposed to do to get your Km. The Km is such that maximum weight goes into WC. So you are splitting your W into two parts, and depending on what data points you are making mistakes on. Right? The data points you don't make mistakes on contribute to WC. The data points you make mistakes on contribute to WE. And you want to see how much larger you can make WC than WE. So basically that's the classifier you have to find. So for that you use some kind of a weighted classifier. So one way of achieving this is to do the following. You assign weights to all the data points. Now what you do is you go and sample from these data points according to their weights. You create a new training set by sampling from these data points that was given to you according to the weights. So what does this mean? Points for which the weight is higher will get sampled more often into this data set. Points for which the weights are very low might not even appear in the data set. Right? So if a point appears multiple times in the data set, then when you are trying to minimize the training error, you are likely to get that point correct. So instead of directly using a weighted training algorithm, people simulate that by sampling from the data with the weights. Okay? So what has happened, unfortunately, because of this, it kind of tends to confabulate bagging and boosting in the minds of people. And if you look at some of the data mining textbooks, especially some of the earlier data mining textbooks, okay, bagging and boosting will be described in a very similar fashion. Right? What do you do in bagging? Whenever you add a new classifier, ரொம்ப நேரமாக போயிடுச்சா இல்லை பரவாயில்லையா 5 minutes ஆகும் அப்புறம் பார்த்துக்கலாம். So in the older textbooks, how they describe is what you do in bagging is every time you generate a new sample, you sample uniformly, right, with replacement, right, you sample with replacement. In boosting, the difference is every time you generate a new sample, you use the prediction error from the previous time. That is the only difference between bagging and boosting, right. Operationally, if you think about it, so that is the only difference between bagging and boosting. But then boosting is inherently serial, and then there is this error minimization property, right, but that never comes across, and people just tend to think of boosting as bagging with a different sampling distribution, right, but that is incorrect, right. The fundamental principles of the two things are very different. Okay. So we have found Km now, right. So we all know how to find Km. You do some kind of weighted error minimization, you find Km. So what is next? What is next? We need to find alpha m, right. See, regardless of what value of alpha m you choose, the minimizer is the for Km is the one that gives you maximum weight into WC. correct. But then having chosen a Km, I now have to choose an alpha m, that gives me the error reduction. So how do you go about doing that? In fact, we can do our so set is equal to 0. So alpha m is essentially half ln 1 minus the error rate, right. So error rate is essentially the weight of the data points on which you are making a mistake divided by the total weight, right. So this is for the kmth classifier alone, right. WE is the data points on which the mth classifier alone makes the error, not Cm but Km, okay, correct. So that is what we divided these things into, right. So this is the thing where Km makes a error, right. So essentially that, so the data points, and so essentially it tells you how good the classifier is. If the classifier is really good, right, not just on the data points that you are interested in but on the entire data set, right. If the classifier is very good, then the weight will be high, right. If the, in fact if the classifier has a error of 0, what will happen? Weight will be infinity, because that is the only classifier you will need, right. If you have an error of 0 on all the data points, why do you need other classifier? Just that one is enough, right. But then suppose it has a very high error close to 1, weight will be 0, okay. So depending on how good the classifier is, this weight will vary, okay. And then anything else that you have to do? I have found Km, I have found alpha m, what do I have to do now? I have to change my W's now for the next stage, right. So what is my Wi? It's e power minus yi Cm minus 1 xi, right. So now it has to become e power minus yi into Cm xi. So what is the right best way to do that? Just multiply the existing W by e power minus y into Km xi, right. Does it make sense? After you have done that, you come here, okay. I don't want to erase that part. Right. So because you need the alpha m here for your update, so once you find the alpha m, you come back here and change the weights of all the data points by this amount. Okay. Does it make sense? So that is a plain simple version of AdaBoost. Right. So, in fact, we can show that the exponential loss function is very closely related to the deviance, right, and in fact, an equally popular version of boosting called logit boost exists, where we actually use the deviance, the logistic function, right, the log odds function that we used for logistic regression. You can use the same error function and then derive all the update rules that we just did for the exponential loss function. You can do the same thing for the logit function, the log odds function also, and you can come up with similar update rules. Okay. So, the reason AdaBoost is so popular is because it yields such very simple updates, right. So, if you think about it, all the computation you do is, okay, you find a classifier that minimizes this weighted error, right, then you come back and compute this alpha m, right, and then you go back and change the weights and then repeat until you are happy with the performance of the total classifier, right. And both with bagging and boosting, the combine both, you start basting things anyway. So, to do both, decision trees are very popular classifiers for this. Okay. In bagging, it seems to make sense, right. Why you want to bag decision trees? They are notoriously unstable. So, if you bag decision trees, you get more stable estimates. Why would you want to why do you want to boost decision trees? Are they weak classifiers?
Initially with less number of branches, then
What's that?
initially with less number of branches.
Exactly. So, what you do with decision trees, in fact, you can do the most extreme thing. You can just have one node, just have the root node, right? Right. One node. What can you do with one node decision tree? Yeah, that is somewhat like linear, right? Yeah, so somewhat like linear, I agree, but people call it decision trees, right? So, one node decision tree, because of the way I choose which feature I pick, right? I will use information gain or Gini index or one of those things. Okay, I will at least get 50% classification, right? Otherwise, I would not even split, right? On that 50%, I will be better than 50%, right? I will be better than random, even if I split on one node, right? So, I will split on one node, and or maybe if the performance is too weak, I can do a 2-level tree. Okay, these are called decision stumps. I do not build a full tree, but it is like chopped off at a very close to the root, right. So, 1 or 2 levels of the tree, so they are weak classifiers, and they take very little time to estimate, right. I can do many of these very quickly, right. Essentially what I do is I boost these decision stumps. Okay. In fact, there is one result in the book, if you look at it, right. So, I do not remember the exact scale on the y axis, but the x axis is the number of levels of boosting that they do, right, and so on and so forth, number of levels of boosting that they do. So, 100, 200, 300 and so on and so forth. So, a single stump, right, gives some performance level at that height, okay, just one stump, the best single stump gives you a performance there, and they trained it on the full data and they get a performance here, and this is like a 244 node tree, 244 nodes. It is a fairly complex tree they built, and that is the performance that they get, right. And then they did boosting. They start here obviously with a single node, right, and then they do boosting, and then they find that the tree, the performance just keeps improving as they do AdaBoosting. Remember, and these are all single node trees, okay, they are all single node trees, and so essentially when they reach 100, that means they have only 100 nodes basically, and they are way better than the 244 nodes that you get with a single tree, right. And when they reach 244 nodes, they are like more than twice as good as the single tree they built with 244 nodes, okay, because the objective function you are minimizing is something very different, right. At every stage you are changing the function, and you are focusing your efforts on actually getting to the harder parts of the space, right. So, that essentially is the thing, right? It is magical. In fact, this is more dramatic, it is something like this, but look at the book for the exact figure, right. Right, so this is really amazing. Boosting is very powerful, and in fact I will talk briefly about random forest in the next class, which is you do not even have to do any decision making, right. You do things randomly, but then do a lot of them, right. That is also very powerful. So random forest is not a boosting technique, by the way. Random forest is a bagging technique, right, but then that is also very powerful.